Just stay here. Today we're going to be talking about comparators. Comparators are a circuit that use an op-amp or something similar to compare two input signals and basically give two different outputs depending on which one of the input signals is larger. These are fairly simple circuits. We have an op-amp, inverting, non-inverting input. We have some V in. We have a reference signal, and we have V out. You'll notice there's no feedback in this circuit, so the output signal, V out, is simply given as the open loop gain times V reference minus V in. And of course that's only true if the output is between VEE and VCC. So this is going to be VCC if V out is greater than VCC, and it'll be VEE if V out is less than VEE. So this is basically always going to have a signal that's shoved up at one of the rails. It's either going to be VCC or VEE. And we can look at this. If V reference is bigger than V in, then this is going to be positive, this is going to be really positive, and we're going to get a VCC for an output. V out equals VCC. And if V reference is less than V in, V out will be VEE. So here's the two conditions. V in smaller than the reference voltage, we get the positive output signal. V in bigger than the reference voltage, we get the negative output signal. Two rails there. So what does this do? Let's assume we have an input signal, some function of time, voltage, there's VCC, there's VEE, and maybe we have a VN, and let's put a reference voltage here. So there's the input signal, the reference voltage, VCC and VEE, and what we said is the output voltage. So if Vn is smaller than Vref, so Vn is smaller than the ref here, we're going to have the VCC output. So we're going to start out with VCC, and then at this point Vn is going to become bigger than Vref, so that's going to give us the negative output, and that's going to keep going until we cross this again, and then we're going to jump back up to the positive, and that's going to go until we cross it again, go down until we cross it again, and then go back up. So we have an output signal, V out, it's either VCC or VEE, and it's VCC when the input signal is below the reference, and it's VEE when the input signal is above the reference. So that's what a comparator does. It takes an input signal, we either have VCC or VEE as the output. And that's useful if we're trying to control things, say a thermostat. If you set the reference voltage so that it's a reference temperature, so you set it to 72 degrees Fahrenheit, and if the temperature in the room is above 72, we turn the heat off. And if it's below 72, the comparator turns the heat on. So it's a very useful circuit. There's one sort of interesting effect, though, with this that can happen. And let's kind of zoom in to this region here. And let's blow that up a little bit. So we have the input voltage and the Vref. And now let's assume the input voltage is a little bit different than that. Instead of being something smooth like this, let's assume it's a noisy signal. So it's bouncing up and down. So it's not very stable. There's noise on it. And when we get into this particular region here, you'll notice Okay, we start out with the input voltage below, so we're going to be at VCC. We'll put that on here. So we're starting out low, so we're at, let's say, VCC until we get to this point here. And then we drop down. But then right here we cross it again, so we're going to jump right back up again, and down, and up, and down, and up several times, until we finally wind up down. So this noise here can cause it to turn on and off and on and off and on and off many, many times when it's very close to this. That's probably not a great thing. If it's your furnace and it's sitting right around 70 and it's turning on and off and on and off and on and off, you're going to wear something out. So it would be nice if we could protect something against that. So the comparator is very useful, but we could have an issue with noise causing it to turn on and off a lot. One thing we might try to do is we have a single reference threshold that causes it to change in both directions. We might consider something where instead of one threshold, we have two thresholds. So here's the time, voltage, and this was the, take this as the nominal Vref, and maybe we have a lower one. And an upper one. So here we have our signal Vin, and when Vin falls below the lower one, then we change state here. If it's going back up, and we don't change state again until we cross the upper one. So here, the noise would have to be big enough at this point to actually cause it to go above the upper one. So if the noise is fairly small there, it's never going to cross that one again. The transition will happen here, and it'll stay in that particular state until it gets over here and crosses this one, and the noise isn't big enough to cause it to bounce around. So we can protect ourselves from that noise by building a circuit that has two different thresholds, one for going to the positive state and one for going to the negative state. That type of circuit is known as a Schmitt trigger. And it pretty much is the standard input on any comparator circuit. And a fairly simple Schmitt trigger utilizes positive feedback to basically split the references. So we have the comparator like we did before, V in, we have V out, but now we're going to put a feedback resistor here connected to the output. It's going to go over, go into the positive input, and then we're going to put a potentiometer, a variable resistor here, so we can adjust this resistance level. So we have V reference, we can change the nominal voltage here, and we have the positive feedback from this. So if we look at that particular circuit, that kind of looks like a Vref with some R1 and R2, and there's some VR that comes out and goes into basically to the positive input there. And nominally that VR is simply going to be Vref times R2 over R1 plus R2, just a voltage divider equation. So we have this nominal VR here. V out, we know, can either be VCC or VEE. There's two possible values there. So now what we need to do is we need to solve this circuit for the voltage at this point here for the two possible values of the output voltage, VCC or VEE. To solve this, we can actually we'll simplify this circuit a little bit. We'll take the output voltage point there and we'll put V out. And there's a resistor here coming down, and that resistor goes across, and we have Vref, we have R1, R2, and this point here is our VR. And we're interested in what VR is for the two possible VCC or VEE. So we need to solve this circuit here. And if we look at this, we can think about this. There is a current I1 flowing through here. There's a current IF flowing down there, and we'll call it a current I2 flowing through here. And we know that I2 has to be I1 plus IF. These two currents come in, they all have to go out there, so this one plus this one has to be this one. So the current I1 is just the voltage difference here, Vref minus VR, divided by the resistance R1. I2, we can do similar, it's VR minus 0 over R2, and IF is going to be V out minus VR over R. So we can put these three currents into our current equation here, and that's simply going to give us I2 is VR over R2 equals Vref minus VR over R1. That's I1 plus IF plus V out minus VR over R. And we're interested in solving this for little VR, which we have in three places, as a function of the output voltage, being VCC or VEE. So we can collect the VR terms. It's VR. We're going to get a 1 over R2 from this side. We're going to get a 1 over R1 and a 1 over R. So 1 over R1 plus 1 over R. And that's going to be equal to Vref over R1 plus V out over RF. So we need to solve for VR, so we'll have to divide by that. And it's a kind of a messy algebraic expression, but we could do that. So we could rewrite that and come out with this. We're going to get VR is going to be this combination of resistors times VF, re-reference plus R1, R2 over the same thing times V out. So a little simpler there. And we could just simply call that A and that B. And then VR is going to be A Vref plus B V out. So the two possible values, VA will be A Vref plus B times VCC, and the lower one will be A Vref plus B times VEE. So there's the two output voltages in terms of those combinations of resistors that we could control. And generally, VEE is minus VCC. So this actually becomes here minus B VCC. So this is some number plus B VCC, and that's the same number minus B VCC. So we get the nominal reference voltage splitting into a Vref plus B VCC and A ref minus B VCC. So we accomplish this splitting of the two thresholds. When the output is high, we go high. When the output is low, we get the low. So we create the two different thresholds for the crossing, and that's the basis of the Schmidt trigger.